Okay, thank you very much first for inviting me. I'm very happy to give this seminar in this nice multidisciplinary environment. So I'm sure that this can be very helpful for different disciplines and hopefully for future collaborations. My name is Ricardo Vinuesa. I'm an associate professor at KTH in Stockholm, and I'm going to talk about artificial intelligence CFD, and I'm going to also mention some aspects of sustainability, which I think are quite relevant given that we have a quite multidisciplinary audience today. This work is funded mostly by SERC, the Swedish Science Research Center, but also by the Göran Gustafsson Foundation, and I'm part of the flow environment at KTH Engineering Mechanics. So I divided the talk into two parts. First, I want to talk a little bit about how AI can be used for sustainability and what are the implications, both positive and negative. And in the second part, I will be talking more about CFD, and in particular, how AI, in this case, convolutional neural networks and other types of neural networks can help with non-intrusive sensing tasks, which are quite relevant for some of the CFD problems that I'm going to be discussing. So I will start with how to use AI for sustainability. By the way, you have my contact information below, including my research group. So if you have any questions, you can always contact me. Because in this first part, I will just highlight some of the most interesting results of this work. But there are more examples and information in that in the publications and in my web. So this started because we wanted to answer the question, basically how can we identify the published evidence of impact of AI on the 17 Sustainable Development Goals of the United Nations, and more particularly on the 169 targets from these goals. And for whoever is not familiar with them, I will briefly introduce them, but essentially these are goals for a sustainable agenda in 2030, developed by the United Nations, and they span a very wide range of topics. And therefore, in order to assess the positive or negative impact of AI on all these areas, we needed to assemble a very broad multidisciplinary team, which you can see in this slide. So we have, as you can see, myself as a CFD person, an applied machine learning person, focused on fluid mechanics, but also we have machine learning experts, we have ethics experts, people with broad expertise in sustainability, energy, the environment, but also on not only ethical, but also legal aspects. And we were also happy to have Max Tegmark, who is a widely known expert in AI sustainability and AI future. So we have a very balanced and multidisciplinary broad team. And as I mentioned, I will talk a little bit about some of the results, but this work was published a bit more than a year ago in Nature Communications. You can see the reference here below. And if you're interested in additional examples and different additional references, please go to that paper. So these 17 goals range from no poverty, zero hunger, the economy, the environment. We divided all these goals into three categories: the ones affecting the society, the ones affecting the economy, and the ones affecting the environment. You can see the distribution here. This is consistent with already existing divisions of these SDGs. And what we did was to analyze each of the targets from all of those SDGs, from all of these goals. And we found that overall, 79% of all the targets for sustainability can be positively affected by AI. And I will give some examples more related to CFD in a moment. And 35% of them can be negatively affected. So AI can be an inhibitor of 35% of the targets. If we go into the three categories, we can see that the environment is the one with highest possible effect from AI. So 93% of the targets from the environment can be positively affected by AI, whereas the economy has the lowest positive impact. And there is quite some negative impact, 30% on the society, which is something to think about. If we look a bit more into details, on the left, you see a figure where each of the SDGs is shown with if we focus on the thinner line first, what we see is the percentage of targets from that goal that can be positively affected by AI. And on the right, we see the negative effects. So for each of the 17 targets, what is the possible, or is the percentage of targets that can be negatively affected by AI? And what we can see, perhaps a quite interesting conclusion, is that, well, there is different types of studies. I mean, we thought that there are studies that are more sound and with quite some years of development, and some studies that are maybe theoretical or even speculative. So we thought that we should look at the types of evidence and the type of publications that one can find in the literature, and we classified all those references that we found into 4 categories, ranging from A to D. So A are the studies which are very sophisticated and that can have a capability to be generalized. And in those cases, we consider a full impact on that particular target of that publication or that study. And then we go reducing that weighting factor all the way down to 0.25, which is corresponding to the studies that are most speculative. And in that case, we looked at, well, studies that perhaps were not so easy to generalize, or maybe the documentation was not so good. And in that case, we consider that only 0.25, so 25% of that target was positively or negatively affected by AI, given that evidence. And that's what the thicker line shows. So you can see that clearly the thicker line, the darker line, is smaller or equal than the thinner one in both positive and negative effects, because the weighting factors go from 0.25 to 1. In brackets, you can see the effect of taking into account the type of evidence. And again, you can see all the details in this manuscript. Perhaps what is interesting, if we compare the cases taking into account the type of evidence and not taking into account the type of evidence, and this is maybe relevant also for this group here, because we are developing AI applications and the type of evidence is connected to how sound the research is. Well, what we can see is that the environment and the society see a bigger reduction of the negative effects when taking into account the strength of the evidence. So perhaps one first conclusion is that the negative effects of AI on the environment and the society are documented, but maybe we would like to have more research, to have more well-founded evidence to really identify those negative effects. When it comes to the economy, actually, the negative effect of AI on the economy is better documented to some extent than the positive effect. So actually, if you see this region here, I think this was one of the interesting conclusions that we found, and we were a bit surprised by it, because there are many studies suggesting that the economy can be can benefit from the development of AI, but many of those studies are perhaps not so well founded, or maybe there should be a bit more sound research to really make that statement. So that, I think, is an important conclusion to keep in mind. And what I will do now, because of course 169 targets is a lot of documentation, a lot of examples, but I will just highlight some important examples which I think are relevant for us, and then I will dive into some CFE applications. So some key results. Clearly, there is a positive effect of AI in SDG 1 on no poverty. I mean, we hope, and it's been proved, that AI-enabled technology is really allowing to overcome current barriers in the context, for example, of using satellite data to track regions of poverty. And that allows us to develop better measures to really help and make sure that these areas are receiving better help. However, this constitutes a double-edged sword, because it's possible that AI helps us to overcome limitations of the technology currently, but it's also possible and likely that it will increase the inequalities, the existing inequalities, which means that there will be a quite negative effect on SDG 10, which is precisely targeting these inequalities. So one of the main conclusions of our study is that AI has the potential to really help in a wide range of areas through new technology that was not available before. But if the barriers to access that technology increase, because now you need a certain infrastructure, now you need a certain training, then it may be that we are worse off than when we started, because the inequalities are increased. So this is very important, and this is, I think, this has implications also for SDG 10 in the context of the current polarization of the society, and in the current COVID-19 times, this is particularly relevant. We all know that when you go to social media, Twitter, Facebook, we are shown the information that we want to be shown, and that's clearly leading to a very strong polarization. So that's something that is worrisome, and that there should be some regulation about it. I will talk about it a little bit later. This also has implications on SDG 16, on strong institutions. And perhaps one important aspect when it comes to regulation is that regulatory oversight should be preceded by regulatory insight. This is a very strong conclusion that we make in our paper. What does that mean? Well, what that means is that if the people making the regulations have no idea about what AI is and what it can and cannot do, then those regulations will leave us in a worse place than having no regulation at all. So I would like to, and all the authors of this article, we would like to advocate for more technocrats and more experts being part of the decision-making process and of the policy development process, now that the EU is also releasing a very relevant documentation on AI policy and AI regulation. This article has been also evaluated by the EU to develop some of that policy. So we hope that we can reach out and that we can start a global dialogue. So experts and people with expertise in these areas can really help to develop adequate policy. This is a related study. This is not exactly AI, but more data-driven methods. It has to do with contact tracing apps that, of course, for tackling the COVID-19 pandemic. But this applies to many other apps that are being developed and will be developed in the future for anything that we do in our daily lives, from bank payments to asking for a loan to getting the place in the kindergarten for our children. All of these apps gather data, and of course, this has to be done in a way that is safe and ethically sound. In particular, the COVID-19 contact tracing apps have implications on SDG 3, on health, of course, but also on SDG 10, on inequalities. And we developed a socio-technical framework, which you can see in this study, in results in engineering, so you can see all the details here, where we considered what are the requirements that these apps need to have from the perspective of the citizens, from the technology, and from the governance points of view, so that they would have minimum impact on the privacy and the safety of the citizens. And perhaps the most important conclusion is that one needs to use decentralized data gathering, and in this sense, the DP3T protocol is the way to go, and many of the apps went that way. And here you can see the scores of several apps that we looked at last year, and also of the EDPB, the European Data Protection Board guidelines. And you can see that the EDPB guidelines are less strict than what we propose in our study for these apps. So I think that, in particular, when it comes to governance, there are many aspects that you can see here. The governance is how the app is being used by the institutions as part of a broader COVID-19 strategy. So that's there are some limitations there in the European regulations, and there should be much more emphasis on those topics. Okay, and this to kind of conclude a little bit this aspect of sustainability, I would like to summarize our findings with this nice picture. I mean, what we find is that the technology, what you can see here is the interactions between three agents: the technology, individuals, and the government. Everything acting over the environment, which is an underlying layer. And the thickness of the lines corresponds to the velocity of change. So you can see that the technology is very quickly, basically advancing and allowing new developments for the individuals. The individuals have needs that go more slowly than the speed at which technology changes. And this, of course, has implications on the government. I mean, the technology requires new legislation, and the individuals have requests from the governments in order to be able to safely handle the new technology. And you can see the thinnest lines here are the governments. So they are actually very, very slow in reacting to this quickly changing world that we live in. And of course, the interactions with the environment, not only when it comes to resources, but also when it comes to positive and negative impacts of the technology development. Okay, so this is, I wanted to use this as an introduction to connect with some of the CFD applications. SDG 11 on sustainable cities is one of the areas with highest potential from AI. And I think that in a way that motivates some of the research that I'm going to be talking about now. Essentially, well, you can see a positive impact of AI on all the targets from this goal. And this is a critical area, sustainable cities, because, well, I mean, 800,000 people in Europe die every year because of the exposure to high levels of pollution. So to have better methods to predict and measure the pollution and to develop better strategies to control those is an essential task. So what we started to do is non-intrusive sensing in urban flows. Here you can see some of our high fidelity simulations. Now I'm diving a bit more into the CFD. This is the turbulent flow around a wall-mounted obstacle. So this is representing one building, although this is at a much smaller scale than in a city. We're not modeling the atmospheric boundary layer. We're just considering here one obstacle. And the idea is to use AI to improve the measurement of pollution. So to use sparse measurements, as you can see here, to reconstruct the three-dimensional flow and also the three-dimensional fields of pollutant concentration. So to train deep learning models to learn from the CFD data to be able to, from few sparse measurements, reconstruct the three-dimensional data. And of course, in a real city, you cannot measure the 3D volume, right? I mean, you need to have sparse measurements. So this is a little bit the motivation of why this area can significantly benefit from AI. And here there's a summary of some strategies for non-intrusive sensing. I will talk more about this later in more detail. What I can show you here on the right are some simulations that we have done. This is our high order spectral element code, NEC 5000, which maybe some people in this audience know about it. Essentially, this code combines the flexibility of finite element methods while being a high order spectral method. So essentially, you can have moderately complex geometries. You cannot do what you would do in an industrial simulation, but still you can have these kind of blocks and buildings. We also have some simplified urban environments with resolution and accuracy very close to DNS, essentially direct numerical simulation. And what we do here is that we use this three-dimensional data where you have two obstacles where the separation is changing, and the separation of these obstacles defines three different regimes. What I'm showing here is three-dimensional vertical structures, which of course are quite distinctly different. This is the skimming flow regime, this is the wake interference regime, and this is the isolated roughness regime. So what we're trying to do is learn how to use this CFD data for non-intrusive sensing, so to train models such that with few measurements, for example, at the wall between the two obstacles or at the walls of the obstacles, we can reproduce the three-dimensional flow. Okay, so I hope everything was more or less clear in this first half, which I wanted to use as a motivation. And now in the second half, I will talk about precisely those spatial predictions, which is what we call non-intrusive sensing. So measuring the flow based on data that is not exactly on the flow, for example, on the wall. And for that, we will use convolutional neural networks, among other techniques. So this now I'm more into the CFD aspect of the talk. What I'm showing here is a turbulent channel flow. There have been many approaches to predict the turbulent fluctuations at a certain distance from the wall. So if I consider a channel, the channel is the flow between two horizontal walls. And if you use the information at the wall to predict the flow above the wall, so to do non-intrusive sensing in a simple geometry, well, there have been many approaches in the literature to do this using linear methods. This is the key aspect here, using linear methods. For instance, linear stochastic estimation or extended proportional decomposition. And what we did a couple of years ago in this article in JFM, in Journal of Fluid Mechanics, is that we use transfer functions in spectral space to predict the flow far from the wall, based on information at the wall, using both linear and nonlinear transfer functions. And we found a quite significant improvement by using the nonlinear transfer functions. Why is that? Well, turbulence is nonlinear, as many of the CFD experts here know. And of course, turbulence relies on the interscale phenomena relies on two types of mechanisms. One that is the superposition, and that's a linear mechanism. So that mechanism can be well predicted by linear methods, but the modulation is nonlinear, and the modulation cannot be very well represented by linear methods. However, we are in luck because, as we will be discussing, neural networks enable nonlinear predictions through the nonlinear activation functions that we are using them. So what I'm showing here is the flow in the turbulent channel at y plus 15. This, for the ones who are not familiar with it, this is basically the near wall region, so the region of strongest turbulent fluctuations. And what you can see on the right is the linear prediction. And you can see that, well, these structures, these streaky structures in the flow are significantly attenuated when using a linear method for that. So essentially, we need to use nonlinear methods for doing these predictions. And what we did was to consider an open channel flow. Open channel is a geometry in which you have a lower wall, and on the top wall you have a symmetry condition. The reason to do that, as opposed to a turbulent channel with two walls, is because the larger scales in turbulent channels have interactions with both walls, and the dynamics of the larger scales is slightly simpler with an open channel. So for prediction purposes, it's a little bit simpler for us. Okay. So we did a DNS, direct numerical simulation, in order to provide good data for our deep learning models. We used our Fourier-Chebyshev code called Simpson. This is a very standard Fourier-Chebyshev discretization developed at KTH. And you can see the parameters here. The friction Reynolds number is 180 in this first case, so it's a low Reynolds number, but it's turbulent. And you can see the domain size and so on. All the information about this can be found in this reference that you can see here. So all the details are provided in this reference, and there are more references and more details that I will be mentioning later. So what type of model do we want to use? Well, first of all, one can look at what is called fully connected networks. And this is a schematic representation of a neural network where you have the input vector on the left, the output vector on the right, the hidden layers in between, and all the neurons from each layer are connected with the neurons of the next layer. We have worked with this in the work by Srinivasan and others in physical review of fluids, so you can have the information here. And essentially this, if you use recurrent networks, as in that study, you can do very good temporal predictions, for example. The problem is that because all the neurons are connected to the neurons of the next layer, the amount of parameters, all these weights and biases that you see here, is huge, especially when you start to work with images. So for that reason, when working with images in computer vision, then it's much better to use what is called convolutional neural networks, which are represented here. This is actually borrowed from the NVIDIA Deep Learning Institute, so I'm already influenced by you guys. And so how does this work? What we have is that we don't connect all the grid points, but we have what is called a kernel here. It's a little window, in this case of 3 by 3. And this window, what it's doing is that it's sweeping across the image and performing a convolution operation. So that convolution operation gives us, from these 9 points that you can see here in the input, just one value in the output. Okay, I will tell you a bit more about it. But essentially, the point is that these convolutional neural networks, they have significantly orders of magnitude fewer parameters than the fully connected networks, and in computer vision they are extremely efficient because they're easy to train if you have enough data, and it can be said that this type of network is basically how AI sees the world, right? So how is it possible for AI to really see the world and identify patterns in the data? So we use this type of network for our non-intrusive sensing example. Remember that the final goal is to do this in urban environments, and that's something that we are currently working on. But what I will be discussing today is the results in a simplified geometry, so in a channel. I'm not considering the obstacles yet, I'm just considering the wall, although preliminary results on the obstacles on the city flow are very promising, and it seems that it works quite well. But let me just describe in detail the approach for the channel. So what we do is that we assume, we take as an input the information at the wall, in particular the two wall shear stress components, okay? And I want to predict, based on a convolutional neural network, the streamwise velocity fluctuations on a plane that is located a certain distance upwards, okay? So what I'm doing is that I am essentially increasing the information that I have, and using just the information at the wall, I will exploit the spatial distribution of the data to predict the fluctuations at an off-wall location. In this case, I am just looking at the streamwise velocity fluctuations, but I will show you also that we have done this with more fluctuations, and of course, with more information at the wall, at the input, then the predictions improve, okay? So let me dive a bit more into what we want to do. And once again, all the details can be found here, in this reference by Wastoni and others, who is a great PhD student in my group. Okay, so, okay. Let me describe a little bit the CNN architecture, the convolutional neural network architecture. Here on the left, you have the input. So we have basically two planes, the two wall shear stress components. And on the right, we have the output, which in this case is one plane, is the streamwise velocity fluctuations. Each of these blocks represent the hidden layers and the feature maps that we're going to obtain after each of the convolution operations that we're going to perform. If we can also talk in the question and answer session about the convolution operation and what it means, but I think that probably it's good to skip it from the main presentation, and we can go directly to more details of the networks. What we have here in the inputs is 128 square grid points. So this is the size of the images that we have here. We're using 6 layers. And the ReLU, the Rectified Linear Unit Activation Function, which is extremely popular for computer vision applications. The numbers that you see here correspond to the number of stacked layers. So if we look at the first convolution operation, which is right here, what we have is a filter which has a depth of 2, because we have 2 inputs, and a kernel size of 5 times 5. And that little window that is sweeping across the images in the first layer has a size of 5 times 5. Later on, we will consider a smaller filter, but in the first layer is a bit bigger, so it's 5 times 5, which means that we have 50 parameters. So my basically my first layer of the CNN has 50 parameters to train. If I was using a fully connected network for this first layer, I would have all the grid points connected to each other, and I would have almost 33,000 parameters. So you can see the significant difference in the number of parameters, and you can see why CNNs are used and preferred for computer vision, because of course, for large images, fully connected networks are just not practical. This is not gonna give you any good result. But convolutional networks are actually very good at identifying features in the data and using those features to perform the predictions. So each time that we apply a filter, in this first layer, we apply this 64 times. So we apply the filter a total of 64 times, and we have 64 stacked layers. And each of these layers identifies a certain feature map. So each of these layers gives us certain features, which in the context of turbulence, these features can be near wall structures, they can be strong fluctuations, they can be negative velocities, and they can be they can be backflows. All of those features are identified by the convolutional neural network. And this is, in my view, the biggest advantage of using this type of architecture. The convolutional networks are able to exploit the spatial distributions of the data. So if the data has a certain pattern, if the data has a certain structure, the convolutional network is going to be able to exploit that, identify those features, and use them to perform better predictions. In the next layer, in the second layer that you can see here, our depth needs to be 64, because we have 64 planes here, but the kernel is smaller. The kernel is just 3 times 3. This gives us 576 parameters, which still is significantly lower than a fully connected network, and we apply a total of 128 filters for the next layer. Something important, because each point here relies on many points from the previous layers. As we go deeper into the network, what we see is that we progressively identify larger features, larger structures, because each data point from here relies on many points from all the previous layers that we have been considering. Therefore, the deeper layers are associated to and are able to identify progressively larger features and progressively larger scales. In a very simplistic way, one can say that the first layers are identifying the smaller scales, and the layers that happen towards the end, those ones are targeting larger scales. This is a bit simplistic, but it's a way to kind of illustrate it. So essentially, this is a bit of a recap on convolutional networks. There are 2 types of convolutional architectures, oversimplifying this a lot. The first one is when the convolutional network has a fully connected layer at the end. And in this example, I'm having a lot of convolution operations, but the final result is just a number or a label. In this case, this is used for a classification problem. So I have an image, and then I apply all the convolutions, and the final result is a label, which in this case is a car. So I identify that there is a car on the picture. But if at the end I don't have a connected layer, if I keep having convolutions all the way to the output, as it is our case, if I go back to the previous slide, the output layer is still, is after a convolution. So the output layer is a plane. It's not one value. It's not one scalar. It's one 2-dimensional plane. Then what I have here is that I can have a classification with a local character. So in this figure that you can see here, the output is not a label, it's a plane, but with classifying the different elements in that picture. I can see what are the cars, the roads, the buildings. So this is what is called a fully convolutional network, because all the layers include convolutions and there are no connected layers at the end, okay? So now, if I apply this to the case of the turbulent channel, what we can see, and I mentioned before that several people, Finar and others, Sasaki and others, use linear methods to do this prediction from the wall to the fluctuations far away from the wall. This LSC that I show on the top is the linear method. And we're going to compare that with the approach from the neural networks, okay? So I'm going to predict the stringwise velocity fluctuations at y plus 15 in my turbulent channel. Remember, this is the region of strongest turbulent fluctuations. And those fluctuations can be observed here in the reference. You can see that there are streaky structures of high and low speed. For people familiar with turbulence, this is a very, very, very characteristic pattern. The linear method sees some of those structures because there is a linear imprint of those on the wall, but the attenuation of those fluctuations is significant, and the small scale contribution to these scales is also lost. Whereas the neural network is able to predict extremely well the reference field by keeping not only the shapes of the structures, but also the modulation and the small scale contributions to it. So neural networks are very promising when it comes to doing non-intrusive sensing in turbulent flows. You can see more information in this work by Wastoni and others. And if I go farther away from the wall, y plus 30, you can see that, well, the linear method is essentially
showing very, very low fluctuations. The neural network still shows very good results, although slightly more attenuated. And if I go farther away, the linear method doesn't give me essentially anything. And the neural network, although it identifies the features of the flow, it already starts to exhibit a certain attenuation, because of course the flow is less correlated the farther away you go from the input. What we also show is that farther away from the wall, by using a larger time step in the sampling, as you can see on the bottom, the predictions improve. So this has to do with how you define your training data. And in a way, your training data, this is interesting because if you're close to the wall, the time scales are quite fast. So you have different snapshots that give you different information, but the same sampling resolution, the same frequency of sampling, farther away from the wall may give you redundant information, because the larger scales far from the wall, they're much slower. And that means that the characteristic time is longer. And with the same sampling, you may be seeing information that is redundant and your training may be less efficient. So this is something important to keep in mind when looking at the type of training data that you use for your networks. And this is the performance of the green is the linear method, and the orange and the blue are the two neural networks for the turbulence statistics. So when it comes to predicting the mean, I mean, the mean is very well predicted, but more importantly, the fluctuations. And as we can see, as we go farther away from the wall, the prediction capabilities decrease, but very close to the wall, we get extremely high accuracy. We get errors below 3%. Actually, I will show you, sorry, I will show you later that we can get errors even below 1%, whereas the linear methods give you much, much higher errors. Okay. So this is when it comes to the statistics. Another interesting extension of this work is to a higher Reynolds number. So everything that I have been talking about has been at Reynolds 180, which is turbulent, but unfortunately it's a Reynolds number where there is no real scale separation. That's why we extended the work to a Reynolds of 550, where one starts to see some scale separation and more characteristically turbulent features. This work, you can see it in arXiv, and this is, we consider a more complete architecture, a more complete analysis, and you can see all the details of the data and the models in this reference over here. Essentially, we still consider an open channel at a high Reynolds number. We consider 3 input velocity fields, so the 2 wall shear stress components and the pressure, and we predict the 3 velocity fluctuations, string-wise, wall normal, and span-wise, at several different locations of the wall. We also consider periodic padding, and if you're interested in that, we can discuss it later on. So we also consider another method, which is this is developed in collaboration with WMS and others, and you can see the paper here, where we looked at the POD. So we do the proper orthogonal decomposition of the fields. And essentially, what we do is that we predict the coefficients of those POD modes. Why is that? This is because the POD modes already encapsulate a lot of information from the flow fields. So if we, in certain cases, it may be more efficient to just predict the temporal coefficients and keeping the spatial distribution from the modes from that encapsulated information that we have. To put it simply, this is a way to give the network more information by telling the network how the modes should look like when reconstructing the full velocity signal. Okay. And what I'm showing here at Reynolds 550 is the fluctuations, the string-wise velocity fluctuations at 2 locations. On the left column, you can see the near wall region. On the right column, you can see y plus 100, which is farther from the wall. The first line is extended POD, which is the same as linear stochastic estimation. So this is a linear method. The third row is the reference. The second row is the neural network plus POD approach. And the last row is the neural network, convolutional neural network methodology. So what you can see is that close to the wall, the prediction with the fully convolutional network is spot on, is almost identical to the DNS. The linear methods, well, they're significantly attenuated. And when I include the POD information, close to the wall, the performance is a little bit worse. However, when I'm farther away from the wall, the POD-based approach is a bit better than the regular convolutional network approach. And this is because of the large-scale information encapsulated in those POD modes. And we will look at this now from a more quantitative point of view. But from the instantaneous perspective, you can already see that the predictions that we can get with the nonlinear methods are really, really accurate, in particular because we're able to reproduce all the nonlinear behavior that we have on the flow. Perhaps not all of it, but we can really have a significant reproduction of those. Okay. So in the next slide, we can see the turbulence statistics, which more quantitatively illustrate what I was mentioning. Here we have the string-wise, wall normal, and span-wise fluctuations. And you can see that the orange is the fully convolutional network approach. Blue is the prediction using convolutional networks and POD. And green is the linear method, is the extended POD. Of course, all the methods exhibit worse performance farther away from the wall, but you can see that the predictions of the string-wise velocity fluctuations are actually extremely good, particularly close to the wall, but even far away from the wall, the results are really good. As I mentioned, with the convolutional network, we get less than 1% error of the when it comes to predicting the near wall fluctuations, which I think is a remarkable result. Even farther away from the wall, here you can see, just using the neural network, we get 33% error, and when using the POD, we get 26%, which it's sufficient to get a good idea of what the large scales look like for in the future designing flow control strategies or other ways of trying to attenuate the pollution effects in an urban environment. Okay. I would like to have a last section, or almost last section, on something that we found very interesting, and it's what is called transfer learning. So transfer learning is an approach where you can use the information learned from one architecture or one model to another one. And I have two examples for you. The first one is at Reynolds Tau 180, which you can see in this reference here. And I think that this can be very helpful for the audience here using CFD and AI. If you remember some slides before, I mentioned that the first layers are more focused on the small scales, and the last layers are more focused on the large scales. What we do here is that we take the model that we use to predict the flow at y+15, so close to the wall, and what we do is that we freeze the 3 first layers, and we only train the 3 last layers to predict the flow at y+50. Okay, so essentially we fix the model for the half of it, and the second half, the one that is targeting the larger scales, that one is left open and free. And what we can see is that we get very similar results, but at 1/4 of the cost. You can see here the training time. So at 1/4 of the cost that it took us to train the full model at y+50. So the information that was learned for the small scales at y+15 is still helpful, and we can reduce the training cost by a factor of 4, which is quite remarkable. Another example, this is, I personally like this very much, because this is one of the first questions that you always get, no? When you're starting to do AI with CFD, is, okay, I can train a model for a very small Reynolds number, but when I want to generalize this to larger cases, what happens, right? So what we did, and you can see all the information in this reference by Guastoni and others, is that we took the data, the weights, so the AI model, developed for the Reynolds Tau 180 case. And we took those weights and started training the Reynolds Tau 550, starting from those weights that we know from 180. And what you can see is that if we, to summarize a bit these figures, if we look at the cost of training the Reynolds Tau 550 with transfer weights and with starting from initial random weights, we can see that our data set can be 25% of the original. In other words, if I use, because of course, here we have a lot of CFD experts, a simulation at Reynolds Tau 180 is significantly orders of magnitude cheaper than a simulation at Reynolds Tau 550. If I can train a network at 180 and then transfer the weights to 550, then I only need to use 25% of the data at 550. I have reduced 3/4 of the simulation cost at 550 by exploiting the information that I have at low Reynolds number. Now, this transfer data, this transfer learning data, this is an extremely, this is very novel, but also has extremely high potential for CFD applications. I think that this is, and we are exploring other avenues to be able to exploit this, but I'm very optimistic with this type of approach that you can see here. And I will be very happy to discuss ideas in the context of transfer learning, because this is very nice. And this is a very recent ongoing work. You can see the preprint in archive here. This is still under revision right now. So what we want to do, so far everything that I have explained to you is assuming that I know all the information at the wall to predict the flow far from the wall. However, in reality, if you remember the picture with the buildings that I showed you at the beginning, I don't have all the information at the wall. I only have few sensors. I only have few measurements. So I need to find a way to do high resolution predictions based on low resolution inputs. And one way to do that is with the so-called generative adversarial networks, GANS. They have become very popular for basically producing high resolution videos and things like that. And what we do here is that we have a network with 2 steps. In the first step, we go from the low resolution inputs to high resolution inputs. And from those high resolution inputs, I can get high resolution predictions. And I can give you just a flavor of the results here. The DNS, this is reconstruction at y+15. The DNS is here on the left. And FD is the downsampling factor. So I go from 4, which means that I have 4 times fewer grid points in each of the directions. So 4 square, 8 square, and 16 square fewer grid points in my input. And you can see here that my input is really, really coarse. I mean, these are just few measurements. And you can compare the prediction that I get with the reference. And the most exciting part is that, yes, I see an attenuation of the fluctuations, but the structures are very, very, very well represented. To me, it's quite amazing that from this, which is telling me nothing, I can obtain something like this, which looks physical, gives me the sizes and the modulation of those scales, and a very good representation of the flow field, well, in a region that is very relevant to the flow. This can be very, very important for applications that have to do with flow control and management of pollution in urban environments. Okay. And then I would like to mention future applications that we're working on in the context of modeling. So for and this is probably quite interesting also for some of the people in the audience. So there are some ideas when it comes to LES modeling and to off-wall boundary conditions, inflow conditions that are being generated with machine learning, structure tracking. This is something that I'm very interested in, so to be able to exploit the information that we have. And we also have quite some work now on model decomposition used for or used through autoencoders. So autoencoders allow us to do nonlinear model decomposition, and it's a very compact representation of the data. And we have been seeing that there is quite some potential compared to more classical decomposition methods like POD or DMD. So this is also ongoing work, and we believe that in the context of the complicated urban environments, it can be quite promising. So I would like to give you a summary of the conclusions, and I think we have some time for questions. I will not try to spend too much more time, but essentially I started by saying that AI can really help with 79% of the sustainable development goals, of the targets from the goals, but 35% of them can be negatively affected. So it's very important to be aware of those limitations and start a global debate that can help us to tackle those limitations. Convolutional neural networks and GANs
through those convolutional networks can really help significantly to predict turbulent flows. We have managed to get less than 1% error for non-intrusive sensing, which is quite remarkable as well. And we are having some possible improvements, like taking into account the structural inclination. We're going to more complicated geometries, and also we're working a lot on the transfer learning strategy. I would like to thank you very much for your attention. I'd like to promote my my research group. You can find here in vinuesalab.com. If you have any questions or you want to contact me, you can always do it there. And I'm very happy to take your questions now. Thank you.